limitations of regression. This will be in 3 parts. I'll talk about outliers, start out talking about outliers, and then I'll talk about extrapolation, and then I'll talk about cause. Start out talking about outliers. For this data set here, we went over this example before, and there's 2 different values here that are a little bit unusual. We have this point here has an unusually low x value. This is the x value here is about 32, and the y value there is 42. So it has an outlying x value. It's actually on the regression line. This point here has an unusual xy combination. It's the point that's probably furthest from the regression line. So that's a different type of outlier. I don't know if it's quite an outlier, but it's a little bit, at least a little bit on the unusual side. It has a higher than average gestation, but a lower than average birth weight. So this was, I think this was Yolanda here. I think this was Sophia. Had as an outlying x value, had a very short gestation, and Yolanda had an unusual xy combination. The above average gestation, but below average birth weight. So we have 2 sort of types of outliers there. Sophia's outliers is called a high leverage point. You think about a lever. Think of the regression line as a lever, like you're trying to lift a stone, like so if you sometimes you use a lever to try to lift something up. So this is like a high. It's called a high leverage point. That's where the name comes from, anyway. And then Yolanda has an unusual XY combination. Okay, so we have those 2 types of outliers. Now, if either of these points significantly affects the slope, it's called an influential point. So I computed the correlation coefficient and the slope and the intercept without Sophia. If we took Sophia's out of there, we have 10 babies. If we just look at the other 9 babies and compute the correlation coefficient and the slope, we see that the slope is not affected at all. But the R is affected if we take Sophia out of the picture. We have a very different value for R. For Yolanda, if we take Yolanda out, it actually affects all 3 of these statistics. The correlation coefficient is actually stronger without Yolanda in there, and the slope and the intercept are different. So we could consider Yolanda to be an influential point. Now, not all books have the same definition of influential. Some books might say they're both influential because Sophia had an effect on the correlation coefficient. But we'll say that if it affects the slope, then it's influential. So Yolanda had a big effect on the slope. It was 5.4 compared to almost 5.9 here without Yolanda. Okay, so that's those are the types of outliers that we'll be looking at. Okay, so next topic is extrapolation. Extrapolation. One thing to notice here, this is the same graph again, but one thing to notice here is that for for a fetus that has been 10 weeks in the womb, it looks like the predicted birth weight is negative, about negative 50. So if we do so after 10 weeks, and that's clearly can't happen, right? You can't have a negative weight. If this green line is our prediction line, and after 10 weeks, we had the fetus weighing negative 50 ounces, and that's clearly not accurate. And so part of the issue here is that we don't really have data for fetuses that are 10 weeks old. All of our data is for babies born after 32 weeks, 32 to 42 weeks. The growth with unlimited food supply follows what's called an exponential pattern. This is a straight line here, right? This is our prediction line. It's a straight line. Growth with unlimited food follows what's called an exponential pattern. So this is maybe I'll do get this other page up here. So this is our straight line pattern here, and then if we do make this a red line. So the exponential pattern, the slope increases over a period of time. So we start out with a gradual slope, and it gradually increases. So this is a typical exponential pattern of growth would be something like that, where you have an increasing slope over a period of time. So that's sort of typical of growth with unlimited food. And so if over a limited time period, the exponential is close to a straight line, but over a longer time period, you either have to use a different straight line, or your prediction is going to be off. We could use a different straight line with a slope that's more gradual here to make predictions, like for example from 10 to 20 weeks. To try to use the same slope for 40 weeks that we're using for 10 weeks is not going to work well. So if you use if you try to make predictions outside the domain of the original of the original data set, that's called extrapolation. So sometimes sometimes you can't avoid extrapolating. For example, if you're trying to make predictions about let's say world population, we're going into the future. We don't have any data about the future, so you can't always avoid extrapolating, but you just have to be cautious about extrapolating. So anyway, that's that issue. So we've talked about outliers and extrapolation. The third thing I want to talk about here is cause. The correlation coefficient really doesn't tell us anything about cause. That's one of the other limits of correlation. It just doesn't tell us. Usually, if you want to try to understand what variable might cause the other variable, you have to think about what might make sense. The mathematics of it is not going to tell you necessarily. If there's a strong correlation coefficient between variables A and B, it might be that A causes or affects variable B, It might be that variable B causes or affects variable A. It might be a third variable affects both. Or if you have, especially if you have a small data set, it could be a coincidence. Okay, so let me give you a question to think about here. In a study of public school students, this is an actual study, I think it was in the Boston area, study of public school students between the ages of 5 and 18 years showed a strong positive correlation between the number of cigarettes smoked per day and lung capacity. In other words, students who smoked the most cigarettes tended to have the largest lung capacity. So what do you think makes sense? Do you think smoking causes or affects lung capacity? Do you think having larger lung causes people to smoke? Do you think a third variable might affect both? Or do you think it's a coincidence? Now this study actually had 4,000 students, or 2,000 students in it, so it's probably not coincidence. I'll give you a minute to think about which of these you think is most likely, whether smoking affects lung capacity. Well, it's not that. I should say that smoking increases your lung capacity. There's a positive correlation. So it's not just that affecting, but it's increasing lung capacity. So does smoking increase your lung capacity, or having larger lungs cause you to smoke more, or a third variable affects both, or and I'll rule out coincidence because it was a large study. I'll give you a little bit of time to think about what do you think makes sense. Okay, so let me let's rewrite this. Okay, so smoking increases lung capacity, larger lungs increases smoking, increased age increases both smoking and lung capacity, or coincidence. Well, I'm saying it's the increased age, because the age range here was 5 to 18 years old, and the 18-year-olds, the teenagers are probably more likely to smoke, and the teenagers are also likely to have larger lungs, not because they smoke, but because they're more mature. They have physically more mature. They have increased age. So I'm going to say it's option 3. Increased age affects both the smoking and the lung capacity. The mathematics of it is not going to tell you. And sometimes it's very difficult to determine cause. There's situations where it's even less clear which variable might cause or affects the other variable, and that's one of the reasons for years it was not clear whether smoking gave people cancer or not. There were some studies that said the smoking caused people to get lung cancer, but there's so many other variables in people's lives, so that if somebody's smoking, maybe and they get lung cancer, maybe it's because they're smoking, maybe it's because they live in a high traffic area where there's a lot of car exhaust, maybe it's because they're eating junk food or something. There's so many variables in people's lives that it's hard to determine cause. So an observational study, you're just looking at you're just observing are recording what people do. Do they smoke? Did they get cancer? And it's hard to say from that type of study. In an experiment, if we were doing an experiment, then you can eliminate other variables, and that makes it easier to determine cause. So, for example, you might tell one group of people they can't smoke, and tell another group of people they have to smoke, and tell both groups of people they have to eat exactly the same foods, they have to live in exactly the same place, make all the other variables the same, except for that one variable, smoking. That's the only variable that's going to be different. And if you have an experiment, then you can determine cause. But the problem is that experiments are not always ethical. A lot of times there's no ethical way of doing an experiment. So it's not really ethical to try to tell people what they can and can't do. So sometimes you're able to do an experiment, and sometimes you can't, but because of ethical constraints. So anyway, that concludes this presentation.